Okay, so what we have been doing throughout, the first nine and a half weeks of school, okay, trying to get us to a point where we can read and comprehend math, all right, and the properties that are presented inside these theorems, because that's going to be something that we have to take with us throughout the rest of our math portion. My college algebra students today, we went through about 4 or 5 theorems, and they were presented as if-then statements, and we had to kind of decipher and analyze what they meant to us and how we apply them, okay? And I don't know how many times I said, remember back to geometry, when we said this in geometry, and we talked about how we learn how to analyze and read a statement and apply a statement. We're now doing the same thing in algebra. So we've been doing that, okay? And the rest of geometry is going to be kind of the same thing, just trying to develop a better way of understanding what is being told to me, okay? And how I can read that and analyze it and basically take the important information out of that and use it correctly, all right? The other half of the course so far has been developing these facts, right? We develop what lines are, what points are, what rays are, planes. We put them together, start talking about adjacent angles, addition of angles, addition of segments, and that starts to build linear pairs and supplementary, and then we get these parallel lines, start talking about that kind of stuff, right? So we're developing all these kind of fundamental building blocks, okay? So it's kind of like I think I use the analogy that if we were to, start building a house, we'd probably order, a bunch of concrete blocks or cement blocks. We'd order some concrete, some stone, a lot of lumber. Okay, we would take all of the small components that make a house, and we'd have them delivered to a work site, right? Okay, and then we would start putting those things together. Okay, well, we've kind of just officially had everything delivered to our work site when we finished section 3-4. Okay, now we're going to start putting those things together. We're going to start figuring out kind of our first now true building block of geometry, and it's going to be triangles. Okay, and we're going to investigate and deal a lot with triangles. We're going to learn a lot about triangles. It's going to help us because when I put 2 triangles together, I get a quadrilateral. Okay, when I put 3 triangles together, I get a pentagon. All right, and so the conglomeration of multiple triangles is going to help us create other figures. Does that make sense? Okay, so if we can understand a lot about triangles, we should be able to quickly understand things about rhombuses and other parallelograms and trapezoids and those types of things. Okay, so the bulk of this course, we have about 9 chapters left. A bulk of those 9 chapters, probably 6 or 7 of them at least, is trying to decipher and analyze all the relationships between triangles. Okay, the number one fact that we deal with in regards to triangles that we can never violate is what we learned today. Okay, and I want to try to give you kind of a visual of how we came across this fact, because I want you to understand that these facts are not just something that somebody sat down one day and said, yeah, we're going to make it this number. We're going to say these 3 angles in a triangle add up to this one number. Anybody know what the number is? 3 angles in a triangle add up to? 180. Somebody just didn't sit down and say, that's what it's going to be. We're going to choose that number. Because why would I choose 180 over 190, right? What makes 180 better? So I want you to see how this kind of all falls into place for us. In order to understand this, we have to have one particular postulate present. Okay, and remember, postulate can't prove, but hopefully we can justify this pretty easily with a picture. If I were to give you that blue line, tell you it's called our given line, and you're going to see when I put the postulate in front of you, the phrasing that they're going to be using is the given line. So it's just some arbitrary line that they put up there. Okay, you know that's existing. You know point P is a point that is not on the given line. Would you guys agree with that? Okay, point P has been removed from that line. The question I have is how many lines go through P? How many lines go through P? What would be the answer to that? Okay, each one of these is a different line, right? This is an infinite number. How many of those infinite lines that go through P are parallel to the blue given line? Just one, right? Does that make sense to everybody? Okay? The same thing happens when we talk about perpendicular, right? There's an infinite number of lines that go through P, but how many of them are perpendicular to the given line? Just one, right? Does anybody remember? We're not going to use this fact very much right now, but it will be something we use a lot later on, chapters like 5, 6, 7, and 8. Does anybody know the relationship between, like if these two are perpendicular, what the relationship between these two slopes should be? Anybody remember from last year? Let me say that I'm going to multiply them together. I'm going to take slope of M times slope of M sub 1. Does anybody know what the product of two perpendicular lines should equate to? You guys remember hearing the phrase opposite sign reciprocals? Okay, you guys know what reciprocals multiply to give me? Any two reciprocals you ever get? That to give me 1, right? That's 2/3 times its reciprocal, which would be 3/2, right? So reciprocals just flip the fraction. So 2/3 times 3/2 gives me 6/6. Okay? 4/5 times 5/4 gives me 20/20, right? If you keep doing that, take a fraction, multiply by its reciprocal, you're always going to get the same number over the same number, right? Okay? Which equates to 1. But if they're opposite sign, one's positive, one's negative, what's that product going to be? Is it going to be a positive or a negative value? Negative value, okay? So you learned last year that perpendicular lines have opposite sign reciprocals for their slopes, okay? Well, a better way or an easier way of talking about that is that their slopes product equates to -1. So right now, these two lines are equating to a -0.97. So let's see if I can get to -1. There we go. So those two lines right there would be perpendicular. Okay, and there is, based off of that blue line being provided for me, there is only one black line that would be perpendicular to it. Okay, through P. All right. So why are we talking about this? Why is this important? Okay, well, let's go back to talking about the parallel lines. So those are parallel. And let me do this real quick just to guarantee that they're parallel. I got to find, there it is. All right. So we agree that those are parallel, right? No matter how far around, I think there's some rounding going on. Yeah, around out to like 10 decimal places, and they both terminate at -1.25. So we do have, indeed, parallel lines. So you see what happened right there. When I went to rounding 2 decimal places, it goes up to 13. Don't let that worry you or confuse you at all. Those two lines, 100% parallel right now. Okay? All right, so if that's the case, those two lines are parallel. Okay? Let's take one of those other infinite lines that go through P and draw it in. You guys agree that that's one of those other infinite lines that goes through P? Okay? What does that become for those two parallel lines? A transversal. Okay, so if that's a transversal, when we have transversals and parallel lines, we have a lot of congruent angles, right? I want to look at just one grouping of congruent angles. I want to look at those two angles with you. Do you know them to be congruent based on their position formula? They're alternate interior, correct? Okay, awesome. Let's hide that real quick. Hide that line at least. And I'll put this line in. Is that another one of those infinite lines that go through P? Okay. But it's another transversal for the parallel lines, correct? Let's look at similar angles. Let's look at these red angles. Are those two red angles alternate interior? Does that make sense? So they should be congruent, correct? All right, so I'm going to put these lines all back in real quick. And what do you see that the blue line, the red line, and the purple line end up creating? They create that triangle, don't they? Okay. Now, the one angle that I'm missing is that blue angle, right? Okay. Well, look up there at P. You see 3 angles up there at P, right? You see a red one, a blue one, and kind of a purple one. What are they all going to add up to? 180. Do you see the same exact 3 angles in the triangle? Is there a blue one in the triangle? Is there a pink one in the triangle? Is there a red one in the triangle? So what are the three angles of the triangle add up to? 180. Okay? Does that kind of make sense? All right? So that's why we have this fact. It's not that we sat down at one point, a mathematician said 180 is a real nice number to use. Okay? It just kind of falls into our lap because of these properties. Okay? So what I want to do today, guys, is I want to prove this with you. Okay? Because a lot of times there's two proofs, so we'll spend quite a bit of time on these two throughout the year. There are two proofs that the end of course exam loves to target. This is one of them. Another one is what we call the isosceles triangle theorem. Okay, and we'll get to that in chapter 4 at some point. But we'll spend a lot of time targeting and maybe dealing with these proofs multiple times, so that when we get to the end of course exam, when they ask that question or if they ask something in regards to that, we have a good understanding of it. Okay. So the first thing we need to talk about is this idea of the parallel postulate. And hopefully maybe you've already written something similar to that down. But the parallel postulate is that idea that if I give you a line L, and a point P that is not on line L, and there's one and only one line parallel to the given line L. Okay. Key word is that we got to have the phrase one and only one. Okay. If I just say through a point not on a line, there is one line parallel to the given line. By not putting that phrase one and only one in, and just replace it with the word one, opens the door for the potential of 2 or 3 or 4. So if I have 4 lines that go through P that are parallel to L, do I still have at least one? Yeah. So that phrasing, that's something we want to get used to. It happens all the time in mathematics. We want to make sure that we understand that those phrases, one and only one, are key to us. They're very important to us. Postulate, one of Euclid's axioms. Okay, can't prove it, but hopefully that GeoGebra showing you all those possible lines and their slopes can kind of help us justify that this makes sense. This is true. All right. Okay. Now, the next slide is the fact that the three angles of a triangle add up to 180. Okay? Three angles of a triangle add up to 180. So I'll give you a minute to write that down. It says the sum of the measures of the angles of a triangle is 180. Obviously, to give you the picture there. And what I've typed there in red is that theorem converted into a if-then statement, into a conditional. Okay? Because I told you that you can do that. Every time that you see a theorem that is not an if-then statement, you can convert it. Okay? And really all this one does, the sum of the measures of the angles of a triangle is 180. So we know we're talking about a triangle. So if you have a triangle, then the sum of their angles is 180. That's how we convert that into that red if-then statement. Hopefully when you do that, when you're starting converting these things into if-then statements, if you find the need to do that, you read your two statements in and start comparing them and make sure that your new wording does not bring in any new concepts, doesn't add anything to what the theorem stated initially, or that you kind of remove anything unintentionally. Okay, so I want to make sure that when I read those two, I compare them, that they say the same thing, and they do. Okay, why do I want to do that? Because the theorem is presented this way, but in the next slide we're going to prove it, and I want you guys to see that when I prove this, how do I know what I'm starting with? How do I know what my given is? Well, my given is going to be just the triangle. You have just a triangle in front of you, and the prove is going to be then there are three angles at 180. Is that okay? So sometimes with proofs, depending on what the if-then statement looks like, you might just be presented with a shape, just a picture, okay? And when that happens, there's really not a whole lot to start with. Okay? There's not a whole lot of information. So we've got to be kind of creative in regards to working through that proof. All right. But what we've got here, guys, would you agree with me if I did this? Let's see if I can. The tablet kind of died last period. So let's see if it's working now. that bottom paragraph there starts talking about what we call an auxiliary line, and we'll get to that in a moment, and defining that and talk about the way we'll use that throughout the year. Would you guys agree that when I have this picture of the triangle, if I were to hide those two legs, is that picture right there the parallel line postulate that we talked about at the beginning, in the first slide? Okay? So when I have a triangle, and I just choose one of the vertices, so they're choosing point B here, okay? That point B is a point that is not on a given line, right? So we should know that if point B is not on the blue line, then there should be one line that goes through point B that is parallel to the blue line, right? Does that make sense? So what we're doing right now is we're implanting that parallel postulate on top of our triangle, but it's going through one of the vertices. That parallel line is going through one of the vertices of our triangle. Okay? I just used the top point B. You could have. Is there a parallel line that's going to go through A? That's going to be parallel to that line right there. And there's going to be one that goes through C that's parallel to that line right there. We could use any one of them. Doesn't matter. I just want to use that top line. I think it makes things a little bit easier, at least to draw. Your textbook and some textbooks will do this. They call this an auxiliary line. You ever been to Lima City and gone into their high school and gone to the gym, and then when you leave I think it's the west doors of the high school, you get in the hallway, and on the plaque in the hallway says auxiliary gym. I open the doors and I walk in and I see another gymnasium. Okay, have you guys been there or seen a school that's like that? Walpock has that. There's a lot of schools in the area that have an auxiliary gym. It's not where they hold their contests. It's not where their games are played. It's where they practice usually. Okay, auxiliary gym. What do you think that means in regards to the gyms that I have, or as a, what would you call it? Maybe another word instead of auxiliary. Or maybe you guys think about auxiliary, you think about your aux cord, right? Okay. Well, if you look on the back of your computer, some computers might have an aux jack somewhere. Okay, AUX, right? It's just an additional port on your computer, isn't it? An auxiliary gym is just an additional gymnasium in that school, correct? Does that make sense to everybody? So you see the word auxiliary, it just means extra or additional, okay? So auxiliary cord is just an additional cord. Auxiliary port, an additional port, okay? Or extra. So here, sometimes they're going to call the red line an auxiliary line. It's an extra line for this process, this proof of this triangle, okay? We know it exists, and we're going to put it in there in a manner that provides us information. So, for instance, there's a lot of auxiliary lines here that exist. Would you guys agree? I keep coming back here to use my tablet, but it don't work. Would you agree that that red line that went through B is an auxiliary line? Is that an extra line? Okay. But that one is kind of dumb to put in there because when I put it in there, it doesn't have any relationship to the triangle or any of the segments that are of that triangle. Okay. The red one that has the arrows on it that they started in the picture, that one there, it's an auxiliary one, it's extra, but it has relationships with the blue line AC, right? The relationship that it has is that's parallel. So when we have to use an idea of putting in something extra, adding extra information to our picture, we want to add information to our picture that is useful, okay? So, we've got the proof here. It already worked out. We're going to go through it step by step with you, okay? Remember, we initially said that if we're going to write this as an if-then statement, okay, so this is the proof of the triangle angle sum theorem. And as an if-then statement, it says if the figure is a triangle. Do you see how that gives me the given of triangle ABC? Okay, that matches up with the if. Okay, then the sum of the measures is 180. Is that right there saying that the three angles of this triangle are added to 180? Okay, so that's usually what they start you with. All right, now the author of our text, I just cut and paste this out of, I believe, our textbook. the one that our class is structured around, they don't write the given down. So if you wanted to come in here and like step 0 and write triangle ABC and then say, well, that's given. That's great. That's awesome. Okay. But the reason they don't write that down is because it ultimately doesn't give us any more information. It's really not useful. They're just saying that that's the picture you're going to start with. Okay. So now my first thing I need to do, okay, is we know that if I just start with that blue triangle ABC, okay, if that's all I start with, that there should be a line that goes through B that is parallel to AC. Okay, because B is not on AC, so there's one and only one line parallel through B to AC. All right, that's the parallel postulate. Okay, so that's what they're saying there. Now, why did we talk about an auxiliary line earlier? Sometimes they will tell you that your reason, or they'll accept the reason of definition. I don't know if I spelled that right. Definition of auxiliary line instead of a parallel postulate. Okay, they might say, you know, draw PR through B parallel to AC, and the reason will be definition of auxiliary line. Knowing there's an extra line there, let's just draw that. Let's just put it in. Okay, so those two options for that first statement are fine. All right, so now I look at this, and the question is, if I look at P to B to C, P, B, C, okay? And then I look at angle 3. They say in our statements that PBC and angle 3 are supplementary. Why are PBC and angle 3 supplementary? They form a linear pair, okay? And linear pairs are supplementary, okay? Angles that form a linear pair are supplementary, or if you want to write linear pair postulate, that's fine, okay? So we've got those two angles, PBC and angle 3 at 180. Now, because we brought in this word supplementary, as always, we want to write what that tells us, right? What does that vocabulary word mean for us? It means we take those two angles, PBC and 3, add them together equal 180, right? That's because of what allows me to go from the vocabulary word down to this algebra. Careful, because this was generated from that vocabulary word. Does it have to be definition supplementary angles? When we classify something as supplementary, we then always say they add for 180 because of their definition. Okay? Now, look at the picture. Is angle addition existing between those things? Absolutely. Okay? But the logic or the reason of why we can say that they are supplementary is because, or that they add to 180 is because of what's defined in the definition. Okay, so now here's another question. Statement 4. Statement 4 says PBC. PBC is the sum of angles 1 and 2. You guys agree with that? PBC, a big angle, is the sum of several smaller adjacent angles that make that bigger angle up, right? Why can I say PBC is equal to 1 plus 2? Why can I say two smaller angles added together give me a larger total angle? That's angle addition. Okay? So angle addition right there. Okay? And now, if we look at statement number 3 and statement number 5, they are the same thing. 3 and 5 should say the same thing. Now, the only part that you see visually that are identical is what I'm going to put in these boxes, right? Those are the only things that are identical, correct? But why are they the same? In that first one, we had PBC in there, right? In statement 5, PBC is no longer there, but now 1 and 2 are there. Why can I do that? Substitution. We said PBC right here is the same as 1 plus 2. So why not, where I see PBC here, rewrite it as 1 plus 2. So we got 1 plus 2 plus 3 now equals 180. Shayla said that's substitution. That's absolutely correct. Okay. And now here's the thing, guys. What those 5 steps actually do for us, I think if everybody looked at the picture, looked at angles 1, 2, and 3, you're all going to say, well, I know those after 180, right? Does that make sense? Okay. But we don't have a postulate or a theorem that says we have like linear triplets, okay? Because if I had linear triplets, why wouldn't I have linear quadruplets? Does that make sense to everybody? But when you see all those angles using the angle addition process, adding up to a line like 1, 2, and 3 do, you're going to have to go through a little bit of a process here. And this process will work. So if I had something like, so that's the line. Let's say I had like angle 1, 2, 3, 4, 5. We know angles 1, 2, 3, 4, 5 are all going to add 180, right? Okay. But to prove that we don't have like a, I don't even know what to call it, a linear quintic postulate or something like that. Quintic means 5. Okay. It doesn't exist, because then if that's true, then it should work for a 6 and 7. So we don't have a theorem for every one of those. Does that make sense? But if I have a theorem for a linear pair, all of these could be generated from that. Okay, and it would go through that process of doing it. So now that's awesome. We get 1 plus 2 plus 3 equals 180. That's kind of close to what we wanted up here. We want that, right? A plus 2 plus C equals 180. So we're almost there. But I need to get A out of there, sorry, 1 out of there and put A in, right? Well, why can't I do that? What do you notice about angle 1 and angle A? They were these 2 angles right there that I'm kind of toggling back and forth, right? They are, I heard somebody say it, they're alternate interior. 1 and A are alternate interior. What about 3 and C? Alternate interior as well. Okay? So angle 1 and angle A are congruent. Angle 3 and angle C are congruent because they're both sets of alternate interior angles. Okay? Remember at the beginning we said that red line was parallel to AC. Okay? So now if I have congruency, I know that these measurements should be equal. And I want to substitute. That's what we talked about. We want to get that measure of angle 1 out of there and this measure of angle 3 out of there. And we want to replace those. Well, the only thing I can do to replace those numbers there, because that's what those are representing numerical values. The only way I can do is replace them with other numerical values. So I can't do that right away because right now that's a shape. I can't replace a value with a shape. So I have to tell everybody that angle 1 equals, or is congruent to angle A, means the same thing for us in regards to their values. Measure of angle 1 equals measure of angle A. Measure of angle 3 equals measure of angle C. That's the definition of congruency. Whenever we go from congruency to equality, that's that definition. Textbook says congruent angles have equal measures. Okay, that's fine. But now do you guys see that now that I have those statements of equality, statement 5 and statement 8 are identical, except for I took 1 out and replaced it with what it was equal to. It's equal to A. I took 3 out and replaced it with what it was equal to, C. And now I have A plus 2 plus C equals 180. It is indeed substitution. And now if I look up at my picture, A and 2 and C are the 3 angles of my triangle, right? Okay. So hopefully we're starting to gain maybe an understanding for these proofs, getting better at them. I know we haven't mastered them yet, and maybe it's by May 31st we still won't have them mastered, but we'll be getting better at them. Okay. I've been doing these for a lot longer than you have. I've had a lot more instruction, a lot more college classes, and I have not mastered proofs. Okay. I can always get better. You can always get better. But hopefully we're getting that way. We're not staying at the same spot we were when we first introduced them, right? Okay. And we're not going backwards, hopefully. But as we do these proofs and walk through and talk through these theorems, I want you to understand that nothing in mathematics did somebody just say, let's let this be equal to 180. Let's look at a quadrilateral. Let's just say the angle's after 360. Nobody says that. Okay, nobody's ever done that. There are physical relationships that occur that force those things. Okay, and that's kind of what we deal with in regards to this class and investigating this class. Now, there are things in mathematics that maybe we do that with. You guys talk about square root of -1 yet? Another class is in Algebra 1. I don't know if that's an Algebra 1 concept. We can't take square roots of negative numbers, but it actually turns out to be a very, very useful thing to be able to try to do, okay, and to actually accomplish. So we define, or somebody did sit down and say, okay, square root of -1 is going to equal this thing. We call it I. And it works, and it makes a lot of nice, neat connections in a real-world application. Okay, so there are times that we sit down and say, yes, this is what I'm going to make this thing do, but we do that in a definition. Okay, saying that 180 degrees is part of my definition of a triangle is false. Okay, this is the definition of a triangle. Nothing else there says anything about 180 degrees, right? Okay. The figure formed by 3 segments joining 3 non-collinear points. Sometimes people say it's a figure formed by connecting 3 points. When I say that, those 3 points could be collinear, and then I don't have a triangle. Does that make sense? Think about 3 points that are all on the same line, connect them with segments, you get a larger segment. You do not get a triangle. So the points cannot be collinear. Sometimes they refer to a triangle as kind of our smallest degree polygon. Okay, degree referring to kind of the number of sides and number of angles. Polygon referring to a segment that's created, a two-dimensional shape that is created strictly with segments. Okay, so for instance, doing that. It doesn't work. Let's go here. File new. And we'll define polygons later on, but sometimes the text in the PowerPoints introduce words that we haven't formally defined. So something like that is considered a polygon, okay? Made up of a bunch of segments, right? Still a polygon. No matter where I move these, it's a polygon, okay? Now, a polygon can't do a couple things. It can't cross over itself, so that's no longer a polygon, okay? It has to be what we call closed, okay? So if I open that up, if I put something in here, could something escape? Okay, so that's not a polygon. And it cannot have curves. So if I did, I don't know how I could do this. See, let's do freehand. Okay, that would not be a polygon because of that curve. Does that make sense? Okay. So circles are not polygons, anything like that. So basically, when we're talking about polygons, we're thinking triangles, quadrilaterals, and then you start getting into pentagons, hexagons, heptagons, octagons, that kind of stuff, right? Okay. When we're talking about triangles, and this is the kind of the bonus of being able to talk about triangles, because once we know a lot about triangles, we instantly know a lot about quadrilaterals. We instantly know a lot about pentagons and octagons and those types of things, all other polygons, okay? Because every other polygon can basically be chunked up into a bunch of triangles. When we talk about triangles, we want to identify, we want to talk about them, we want to classify them, okay? So you guys know these words, scalene. Okay, so we're basically classified based on number of congruent sides. So scalene means no congruent sides. All the sides are different. Okay. Now, that doesn't mean, and this is something we'll get into, that does not mean you can just take any 3 lengths that you want and make a triangle. Because sometimes they'll connect and sometimes they won't. Okay. So we'll get into talking about eventually the relationship that has to occur between the sides of a triangle to actually make the endpoints connect and touch. We have isosceles, okay, it means at least 2 sides congruent, okay. Key phrase here, at least. So what does that mean to us? What's the phrase at least mean, guys? Bare minimum, okay, it's a great way to put it, bare minimum. Could have more, right? So a triangle with 3 congruent sides is still classified as isosceles. It still meets that condition, But a lot of times we like to refer to it as equilateral. All right? Equa, every time you see that prefix equa, it means equal. Every time you see the word lateral, it means side. Okay? So equal sides. Okay? Triangle has, that is equilateral, has all three sides congruent. Okay? So here's a question that I asked. Are or is, let me type it, because you're going to see it on a test. Always, sometimes, never. Equilateral triangles are isosceles. Is that always, sometimes, and never? You know in front of you, you have an equilateral triangle. Can you say it's an isosceles triangle? You can always do that, right? Because if it's equilateral, has it met the conditions to be isosceles? Yes, it's met the fact we've got two congruent sides. Now, let's do this. Always, sometimes, never. Isosceles triangles are equilateral. Always, sometimes, or never. What's the condition needed to be isosceles? You know you have in front of you something that's isosceles. Is there any situations where you could say that it's not equilateral? Right? Okay, so if I have an isosceles triangle in front of me and it has only two sides that are congruent, the third side is different, would that be equilateral? No, right? Okay. If I have an isosceles triangle in front of me, I have two sides congruent, but it just works out that the third side is also congruent. Is it still isosceles? But is it also equilateral? Yes. Okay. So this would be sometimes. Does that make sense? Isosceles triangles are sometimes equilateral. It just depends on what that third side is. Okay. Equilateral triangles are always isosceles. Okay. Those are things, and that's kind of the, you know, that little argument there and process of trying to decipher that is the whole idea. And the reason I talk through this stuff all the time with you guys of how to read statements and interpret them. Okay. And take exactly what those statements are telling you and apply them exactly the way they're telling us. Okay. Because I was always a student that struggled, is a rectangle square or is a square rectangle, that kind of stuff, right? Okay, and those were hard to answer until I realized, oh, well, they're based those questions off of conditions that are met by the object that's in front of me, okay? And if I can realize that and compare it to the definitions that are being provided, I can then accurately describe always, sometimes, or never, okay? We also have the classifications of triangles through the types of angles that they have. If they're all acute angles, we call it a acute triangle. Okay. Now there's some links between acute triangles and these things up here. Okay. But the links usually I need to maybe know what the measurements of the angles are. Okay. Because if it's an acute and they're all different acute angles, then it's going to produce a scalene triangle. If they're acute but they're all three the same, okay. So if I had 60, 60, and 60. Okay, it would actually end up being what we call an equilateral triangle. Okay, so we'll talk about that as we progress through the year. But so some of these things can, you know, identifying it as an acute equilateral or something like that could be done. Okay, actually every equilateral is acute. Okay, but we can talk about obtuse scalene. We can talk about obtuse isosceles. Does that make sense? Okay, obtuse means we have one angle that is obtuse. Why can I not have two angles that are obtuse? Okay. So if I start with, you know, if I have a triangle that has one right angle, that's all I can ever have. I cannot have two right angles. You said that would eat up 180 degrees right away, right? So if I have two obtuse ones, those are both bigger than 90. So like 90.1. Well, that's 180.2 degrees already. And I don't have anything left over for the third angle, and obviously I've violated the 180 degree restriction on the interior angles of the triangle. So you cannot have multiple obtuse angles. You cannot have multiple right angles in a triangle. Okay? Equiangular, again, meaning equal, angle, angular, meaning angle. Okay, so all angles are congruent. If all angles are congruent, think about this. If all angles are congruent, what does each measurement have to be? 180 degrees, right? That's the total. All three of them have to be the same, so they all have to be 60, right? The average, okay? So if all of them are 60 degrees, is an equiangular always acute? That makes sense? Is acute always equiangular, though? No. Okay, I could have, I don't know, 40, 50, and 80, right? Okay? Or no, sorry, that won't work. 40, 60, and 80. 40, 60, and 80. Those would have to 180, right? Those are all acute angles, but they're not equal. Okay, so it's not equal angle. A fact that we're going to talk about is that every single triangle that is equiangular is also equilateral. And every triangle that is equilateral is also equiangular. So a lot of times you might see it this way. Okay. Equiangular if and only if equilateral. Okay, and I should probably put triangle there because we'll talk about other shapes that are equiangular, equilateral, and that doesn't, that condition of basically reading it two ways, left and right, doesn't exist for like quadrilaterals. Okay, for instance, because if I have, you have a square, is a square equiangular? Square equiangular, guys? Are all four angles of a square are they the same? Is a square equilateral? All four sides of the square are the same? Yeah. Okay. So equal means, or equa means equal, right? Or same. Lateral means side. Okay. So all sides of the square are the same. All angles of the square are the same. So maybe we say, okay, well, this is two ways for quadrilateral. But think about a rectangle. Is a rectangle equiangular? Does a rectangle have all four angles 90 degrees? But in a rectangle, do you have to have four sides that are all the same? Can a rectangle have sides that are different? Sides that are different, right? So in a rectangle, equiangular does not imply equilateral. Okay? But in triangles, one of these implies the other. Okay? Hold tight, guys. We still got a couple minutes here. These statements. Okay, now you don't need to write down what a corollary is, but these statements are easily proven through the use of the original theorem. Okay? So these are kind of like the family members of the theorem. The theorem is maybe like the parent. It's the thing that's most important in the family. And these things are kind of like the children of it. Okay? That's kind of the way I view corollaries. Okay? They are easy. Their statements are facts just like theorems are. They're if-then statements. But the proof of them is extremely easy. Think about the one there that says each angle of an equilateral triangle has measure 60 degrees. Well, is that pretty easy conclusion from knowing that all three of them have to have to 180? And if it's equiangular, they're all the same. So 180 divided by 3 gives me 60. Does that make sense? So that proof of that logic of going through and getting that result is pretty straightforward. We already talked about this one here. Okay, you cannot have more than one right angle or more than one obtuse angle. Okay, because then we violate the 180. Okay. This one here, okay, if you have a right triangle, of your 180 degrees, that right angle chews up 90 degrees, right? So you have 90 degrees left over for the remaining two angles. And they have to be acute because we can only have one right angle, okay? So if I have remaining, look at this picture from the board. If I have one right angle here on angle B, and these two are left over, don't these two have to add to 90? What's the definition of two angles who have to 90? Complementary, okay? So that last one saying that the angles of a right triangle are complementary. The acute angles of a right triangle are complementary. This one here, we will talk about this one in greater detail down the road when we need it. So don't worry too much about that right now. I did post a 3.5 homework. It's not going to be due until next week. Okay, we're going to finish this up tomorrow. So if you want to start on that, you can, but not due until next week. Remember the worksheet that I sent out in an email on Tuesday. That is going to be due tomorrow. Okay. Hopefully you've already maybe put a big dent in that or have it completed. Other than that, Have a great day.